Hello again. I want to work for you a mixing problem, continuing the work that we did on Wednesday when we did our Zoom session together. This is a problem from the textbook. It's problem number 36, which is found on page 55. And I've got a rather crude drawing here of a tank that's got some water in it. And initially this tank has got pure water in it, but we're dumping in a brine solution. So what's coming in from this pipe here is brine, that is salt water, at 2 gallons per minute. And the concentration of salt in this brine is 1 pound of salt per gallon of water. That's the concentration. Now the concentration would be the amount of solute divided by the amount of the liquid. So the concentration here is, and the input is 1 pound per gallon, and it's coming in at 2 gallons per minute. The problem goes on to say that initially there are 60 gallons of pure water in the tank before we add anything, and we've got an outflow also. And we have an outflow of 3 gallons per minute. And what's the concentration of what's coming out? Well, it depends upon time, doesn't it? Because as time goes by, we're dumping more and more salt in because we're pouring in a brine mixture. And so that's to be determined what the concentration is, but we're losing 3 gallons per minute in the outflow. And that means, of course, just to observe, 2 gallons per minute coming in, 3 gallons per minute going out. The volume in the tank is going to be decreasing at 1 gallon per minute, isn't it? Each minute there'll be a gallon less in the tank because I'm putting in 2 and taking out 3. Okay. Now what we want to find is the amount of salt in the tank at a time t. Let's let that be x of t. So x of t is the amount of salt in the tank at time t. Now what else do we know about the physical conditions here that will help us set this problem up? Well, we know that the volume of the tank, the volume of liquid in the tank at time t, so I'm going to just call that V of t, is going to be equal to 60 minus t. 60 gallons, which was in there at time t, equals 0, and each minute we lose a gallon. So 60 minus t would be the volume at time t. Now we also know something about how x, the amount of salt in the tank, is changing. And how is that changing? dx dt would be the amount in minus the amount out. And that's how the salt in the tank would be changing. You put some in, you take some out. And the difference would be how we're changing. And we even can quantify that because what's our in? Our in is, now this is salt in, remember. So it's 2 gallons times the concentration of salt in those 2 gallons. And that was given as 1 pound per gallon was the concentration of the input. So it would be 2 gallons times 1 pound per gallon, and the gallons would cancel out. 2 pounds per minute would be the in. We're putting in 2 pounds per gallon. What about the outflow? The outflow would be 3 gallons per minute, but what about the concentration? And this is the key to the whole problem. Once you see that this is how you set these problems up, their solution is usually pretty easy. So the concentration of that outflow would be x of t, that is how much salt is in the tank at time t, divided by the volume of water that's in the tank at time t. So this ratio would be the concentration at time t. Well, then that simplifies a whole lot, and the rest is pretty routine. So what we have here, dx dt is in minus out, is x prime, that's dx dt, is 2 that's the n, minus 3, and x of t would, I'm not writing the t variable with that. I'm not putting that in function notation, but you know that x is a function of t. So it'll be minus 3x over the volume 60 minus t. 3x over 60 minus t. So there's the differential equation. Now, what kind of a differential equation is that? Well, it's not going to be variable separable, but it will be a linear equation. Now, to solve a first-order linear equation, we find an integrating factor, but to find the integrating factor, we've got to put the equation in the right algebraic form. So let's take this differential equation, and let's multiply through by the 60 minus t, and that gives me 60 minus t, x prime is equal to 2 times, see the 2 here, times 60 minus t minus 3x, because that had a 60 minus t in the denominator. And then I'm going to transpose the 3x, and I'm going to get the form right, because this is almost but not quite the right form for a first order linear differential equation. I divide by 60 minus t, and I have x prime plus 3 over 60 minus t times x equals 2. The coefficient of x, when I get this form right, the coefficient of x is the thing that we've called uppercase P of x. And so I see that P of x is going to be 3 over 60 minus t. That's just an observation from looking right here and seeing what the coefficient of x is, 3 over 60 minus t. And so we know that the integrating factor can be found as rho of t, which is e to the integral p of t dt. And when I perform that integration, I get that rho is 60 minus t to the negative 3. And I would strongly suggest that you're doing this on paper yourself and verifying every step along the way. So what do we do next? Well, next we multiply by the integrating factor that we just found. So multiplying by the integrating factor, we get this line, and I'm, I guess, not inclined to read this whole thing to you because you can read, so I'll just kind of show you where it is. And the left-hand side, we hope, is the derivative of a product. Now, what would that be the product? What product would that be the derivative of? Well, I'm thinking product rule for taking derivatives, and I'm looking at this first term, and I see that I've got a 60 minus t to the negative 3 and an x prime, and I know the little mantra that I repeat for integrating products, or for differentiating, products, is the first times the derivative of the second. So if I had a product where this was the first and this was the second, first step would be done. If I had such a product, the first times the derivative of the second would look just like this. So let's just see if this works. I think the product whose derivative is the left-hand side here, I think is x times 60 minus x to the negative 3. And I want you to see where I got that. You know, that's not hard to figure out. I just look at this form and I see what would give me this if I had a product and the derivative of the product looked like this. What would that product had to have been? And it would have to look like this. And then I can get out scratch paper and check and make sure that the derivative of this thing with respect to t, and that's what this operator means, is my left-hand side. That is the case. So if I integrate left and right-hand side, of course this is going to be a differential d parentheses x times 60 minus t to the negative 3. So if I integrate, I get x times 60 minus t to the negative 3 on the left-hand side, and then I'd have to integrate this thing on the right, and so I would get 2 times 60 minus t to the negative 3, and it's an integration by substitution, and I pick up an arbitrary constant, and then more calculus kind of manipulation here. X times 60 minus t to the negative 3. The left-hand side is this new right-hand side. Simplified this by getting rid of those negative 2's. And wow, here is a general solution to my problem. Now, it's a general solution because it contains an arbitrary constant c. Do we have an initial condition in this problem? Well, we didn't state it as such, but we do have an initial condition. And the initial condition is that the amount of brine, that would be x, the amount of salt, excuse me, the amount of salt, which would be x of t, at time 0 was 0. We started out with pure water in that tank. So we do have an initial condition, x of 0 equals 0. And if you'll use that initial condition in the general solution, here's the general solution, so use the initial condition, that would be 0 is equal to 60 plus c times 60 cubed. You'll find that c is negative 1 over 3,600, which is what that is. And when I replace the arbitrary constant c with this particular value, I get a particular solution, and that is x of t is equal to, and once again, you can read it. Now, you can finish that problem on your own. What is the maximum amount of salt ever in that tank was the next part. This was the a part, was to find the x of t. So that's the a part that I've done for you. And the b part is max value of x of t. And you would find that by finding out, just using your extrema theory from calculus, probably calculus 1, because that's you use differentials to find where x of t is a max. And you'd find the t where x of t was a max, but the question is, what's the max value of x of t? So once you find out the t that makes it max, you'd substitute that t into the equation here at a and find out how much salt, the most salt that was ever in that tank. So pretty nice problem. Mixing problems can be challenging, plus they can be a lot of fun. This is a short video today. I mean, I aim to make all of these short, and that never happens, but I think I'm going to quit and make another video for you later. So let's end this one right here. Thank you very much for your kind attention, and have a good day, and we'll meet again soon.